Now that you've learned about the nomenclature of alkenes and the synthesis of alkenes, we're going to go on to the reactions of alkenes, which are quite a lot. There are a few things to remember when we talk about the reactions of alkenes. The first is that almost all the reactions of alkenes are going to be addition reactions because alkenes are what we call unsaturated hydrocarbons. Unsaturated meaning that they can actually take in more molecules or atoms, and once they do, then they become saturated. So the alkenes are considered unsaturated, so addition reactions are common for alkenes. The other kind of reactions we will encounter are oxidations. These are slightly different than the addition reactions, so when we get there, we'll talk about that. And the third thing to keep in mind is that alkenes themselves are nucleophiles and they will react with electrophiles, okay, because alkenes have the double bond, and so they will react as nucleophiles with electrophiles to give the addition products or the oxidation products. The reactions I'm planning to cover in this portion are the addition reactions, which are going to be the hydrohalogenation of alkenes, which is addition of HX. Now remember, X is halogen in organic chemistry. Then we'll talk about halogenation, where you add any of the halogens, which is group number 7. Hydration of alkenes, addition of water. Then there's the Hallow Hydrant formation, where you add a halogen as well as water. Then we will also synthesize diols. Now this is kind of similar to hydration, where in hydration you're adding only one alcohol, but in diols you're adding 2 alcohol groups. Then we'll talk about carbene addition. Now carbene's a little bit different than any of the intermediates that we've learned about carbon. So again, when we get there, I will explain this a little bit more. Then we will talk about epoxides and then hydrogenation. Hydrogenation is addition of hydrogen, which is also considered a reduction on alkenes. It's still an addition reaction though. And then lastly, we will talk about oxidative cleavage. Okay, so these are the reactions we plan to talk about. Here are the reactions in terms of their structures. So here's your alkene. I've taken a very simple alkene, 2-butene, very symmetrical, nothing to talk about over here, but I just want to show you a little bit about all the reactions that we'll be covering. So the first one here, hydrohalogenation. So you add a hydrogen as well as a halogen. Halogenation, adding one molecule of a halogen, which means 2 atoms of a halogen. Hydration, adding water, HOH, so H2O. Hallow hydrant, so you're now adding a halogen as well as an alcohol group. Then here is the diol formation, and here are 2 alcohol groups. I want you to note that in all of these cases, whatever is being added to the double bond, which means that it's a 1,2 addition, or as we say, it's adjacent carbons, okay, alpha, beta, 1,2, but these are all getting added to the double bond. Okay, so and the final product, there is no double bond there, addition reactions, right? And then here's the carbene addition. The purpose of carbene additions is really to synthesize cyclopropane rings. Okay, and you can see it's a very small ring over here. We've talked about the fact that cyclopropane rings are highly unstable and very high in energy, okay, because of the angle strain, but you can still make them. Okay, so this is how we make them, using carbenes. And then here is epoxide. Epoxide is also a 3-membered ring, but now you actually have a cyclic ether, carbon, oxygen, carbon. So this is a cyclic ether, and we've synthesized ethers before in SN1, SN2 reactions. In fact, most of the compounds we synthesized were ethers, but now we'll be talking about a cyclic ether. And epoxides are very specific in their nomenclature, meaning it's a 3-membered cyclic ether. So that's epoxide, so we'll make these. The last addition reaction that we have is that of reduction. So we're adding hydrogen, and that's why you don't really see any other heteroatom over here. And then finally the oxidative cleavage. And you can see, looking at this reaction itself, that there is something different going on here. First of all, you started with 1 molecule and you end up with 2 molecules, okay, over here. And that's the part of the cleavage, which means that something is getting broken. And the oxidative part tells you that there is oxygen being added here. So these are all the reactions that we will cover. A little bit about the general mechanism. We will cover the mechanism individually also as we go on for all the reactions, but just to get you started, okay, for some of the mechanisms, because there is a general trend for all the addition reactions. So first of all, again, alkene is the nucleophile here, Whatever reagent you're going to be adding is the electrophile. Okay, and the alkene is the nucleophile because alkene has the double bond, which is electron rich. Okay, and so here is a reaction. And here is the alkene, which is the nucleophile, and here is the electrophile. This is HX, and if you can think about HX as being HCl, hydrochloric acid, then it'll be a little bit easier for you. So if this is HCl, then this is the base, okay? Because this is the acid, this is the base. So which means that your electrons will transfer from the base to the acid. Now, because we're talking about a traditional acid over here, HCl, which means they are proton donors, the double bond here will go for the proton. Okay, now remember it's a double bond that's going. There are no extra electrons on carbon, either one of those. The electrons reside in the double bond. So you have to start the arrow from the double bond, pick up the proton, and then the proton leaves with its electrons on the halogen. And then this is what you get as an intermediate, which is a carbocation. So now you have these two carbons. Now remember the bond that we used to pick up the hydrogen, those extra electrons, those are right over here with the new bond with hydrogen. You have to place the hydrogen either on this carbon or this one. Okay, because that's where the bond is breaking. So hydrogen can go on either side of the carbon. Right now we're going to go ahead with the left over here, but later on you will see that things can be a little bit different. So one of the carbons will get the hydrogen, the other one will get the carbocation because it has fewer electrons now, or less electrons, and then here is the conjugate base. So which means now we've reversed everything. Now the carbocation becomes the electrophile, okay, because that is electron poor. The conjugate base now is your nucleophile. That will go ahead and attack the carbocation, and here's your addition reaction, HX, HCl added. Okay, so it's really all about acid-base reactions, electrophile, nucleophile, and if you want to think about it from Lewis acid-base perspective, any one of those will work. The other thing I want to mention over here, okay, is the fact that there are two kinds of alkenes. We've talked about this before also, but just a little review, is that there are two kinds of alkenes, symmetric alkenes and asymmetric alkenes. In symmetric alkenes, the double bond is symmetric, okay, which means that it has equal number of hydrogens and carbons, okay, and so this is what a symmetric alkene would look like. It would be fine if it was cis also, okay, it doesn't really matter because even then you will have one carbon, one hydrogen on one double bond, and one carbon and one hydrogen on the other double bond, on the other carbon. So it will still be symmetric, whether it's cis or trans, it doesn't matter. Here, however, this is asymmetric double bond because now on the double bond on one carbon, you have carbon and hydrogen, whereas on the other carbon, you have two carbons, okay? And so this is an asymmetric alkene. Both of these represent the same structures. Over here, I just removed the hydrogens, okay? Because you have to be able to see structures without the hydrogen. So the right side is kind of what it looks without the hydrogen. Anyway, this is not new to you. In any case, so remember that there are two kinds of alkenes, symmetric and asymmetric. So let's talk about the first addition then, hydrohalogenation. Okay, and hydrohalogenation, we will cover this both for the symmetric alkene as well as the unsymmetric alkene. Okay, as we say, because the addition is different for both of them. So here is 2-pentene, which is a symmetric alkene because both of them have a hydrogen and a carbon, a hydrogen and a carbon attached to it. So when you add HBr to it, then you end up getting two products because at one time, the H can go to the left carbon, okay, or at one point the H can go on the right carbon, all right, and so the bromine then is left to go on the other carbon. So you end up getting two products, which is 2-bromopentane and 3-bromopentane. And sadly, you can't do anything about it. So which means that if you take 2-pentene and you do the addition reaction with HBr, hydrobromic acid, you are going to get these two products in equal quantities. If this was symmetrical, for example, if this was 2-pentene, 2-butene, then it wouldn't really matter because if you look at the nomenclature of them, they would be both same. However, when we go towards the unsymmetric alkene, now things are going to be slightly different, okay? And In case of asymmetric alkenes, we follow what is called Markovnikov's rule, and obviously Markovnikov was the one who came up with this. And what he found is that if you take an asymmetric alkene, so for example 2-methylpropene, where one carbon has 2 hydrogen and the other carbon has 2 carbons in it, then if you add HCl, then invariably the carbon with the more hydrogen is going to get the hydrogen, all right, and the carbon with the less hydrogen will get the chlorine, all right. So carbon with the more hydrogen gets hydrogen, and that is called Markovnikov's product, all right. And the other one, in which the chlorine is going to go to the carbon with more hydrogen, is called the anti-Markovnikov's product, which in this case does not even form, okay, which means that the only product that will form is going to be the Markovnikov product. And again, Markovnikov addition is where hydrogen goes to the carbon with more hydrogen. That's Markovnikov's rule, and we follow it, okay, follow it in the sense that it is true, okay, and we'll talk about why it's true. So initially when Markovnikov came up with this rule, the mechanisms were not quite understood, okay, at that point. But once the mechanisms had been established, it is easy to figure out why we would get Markovnikov's product, okay. So here, let's go ahead and write the mechanism now. So when HCl adds on to 2-methylpropene, you can get 2 kinds of carbocations, because the hydrogen can go to the left carbon, or the hydrogen can go to the last carbon over here, okay, the carbon with more hydrogen, because remember, this is the double bond that's attacking the hydrogen. So hydrogen can go on either one. So here is the top one, okay, where hydrogen goes to the carbon with more hydrogen, forming this wonderful carbocation. And then here is the other attachment where hydrogen goes to the carbon with more carbon instead of hydrogen. And then this is the carbocation you get. And so looking at these two intermediates, we know from SN1, SN2 reactions, especially SN1 reactions, that tertiary carbocations are way more stable than primary carbocations, and of course tertiary are the most stable from secondary and primary also. So this carbocation will be formed a lot more, and therefore this will be the predominant product, which means that now when the chloride adds, it will add to the tertiary carbocation. However, the primary carbocation never forms because it's not stable, okay, and hence you get the Markovnikov product, okay, when you have an asymmetric alkene, purely because of the stability of carbocation. One of the things that we've encountered before also in SN1 reaction is rearrangement of the carbocation. And since we've seen the mechanism now for the addition on alkenes, it is primarily through carbocation formation. So which means that we have to look out for the possibility of rearrangements. So let's take this example where we have 3-methyl-1-butene, 1, 2, 3, 4, okay, 4 carbon. And then here is the alkene, and you add hydrochloric acid to it. And what you would expect is that the hydrogen will add on to the carbon with the more hydrogen, and the chlorine will add on to the second carbon over here, which is this product, okay? So 2-chloro-3-methyl-butane. This is the one that you're expecting. However, you do the reaction and you end up getting one more product, which is 2-chloro-2-methylbutane, which means that you got the addition on this carbon of the hydrogen, which you expected, but the chlorine did not add over here. The chlorine actually added on the next carbon over. So then you have to start thinking about, how did I get this product? And it is approximately 50-50 mixture. So which means that there is something serious going on over here. It's not just a minor product, it's quite the major product too. So we have to look at the mechanism again, okay, for this one, and see what is possible. And so let's start with the mechanism here, with the double bond attacking the hydrogen, picking up the hydrogen here and forming the carbocation. But then what happens here is, because this is a secondary carbocation, you can get a hydride shift, okay, from the next carbon over to this carbocation, and so then you will end up getting a tertiary carbocation. And as we know from before, is that tertiary carbocations are more stable than secondary carbocations. And so this kind of a hydride shift leads to more stability of the carbocation. Once this happens, then you end up getting the second product, which you were not really expecting because we did not think about rearrangement before. And then here with the secondary carbocation, you can also get addition. Now secondary carbocations are fairly stable, so you will still get some product. If it was primary, you may not have gotten a lot of product. It would be probably a minor product. But because it's a secondary carbocation, both of these products are almost equal in quantity. And this happened only because of the rearrangement, that you ended up getting two products. If there was no rearrangement, obviously you'd have only one. So, and remember again, the rearrangement happens only to give the more stable carbocation. Otherwise, rearrangement is not going to happen. The other thing you need to remember is that the rearrangements that you do are for small things like hydrogen, methyl, and phenyl. Phenyl is a little bit of a big group, but you can have a hydride shift, a methyl shift, and a phenyl shift. You can't shift ethyl groups or big groups like that, okay, or any other thing. So those are the shifts that you will get, all right? And again, the rearrangement is primarily to give more stability. The next addition reaction is halogenation. Halogenation is, of course, addition of a halogen. Bromination and chlorination are usually the two most common molecules that are added to give the dihalides. Fluorine is very reactive, and I2 or iodine does not really add very well. Okay, remember iodine is a huge molecule, and so it's quite stable on its own. And then fluorine is too small and it's very reactive. So it's preferable to do bromine and chlorine additions only. Also from our previous understanding of SN1, SN2 reactions and substitution reactions, you know that bromine and chlorine are more versatile in reactions than fluorine and iodine can be. You can use them as leaving groups, and so they make for really good starting materials. So this is a very good way of making a starting material for SN1, SN2 reactions. So in any case, so bromine and chlorine are the ones that we will work with. Note over here with the qualitative test, I will talk about that in a minute, okay, with bromine. So anyhow, here's the addition reaction where you have an alkene. You add chlorine to it, and chlorine adds 1 and 1 or a 1,2 addition of chlorine happens. Now, there are a few things that are important. For example, when we talked about the addition of HCl or hydrohalogenation, the addition was Markovnikov addition. Now, in this case, the important thing to remember is that the addition is a trans addition. So what does a trans addition mean? This has to do with the mechanism of the reaction. So here, let's see this. If you have, say, cyclopentene that you're working with and you add bromine to it, this is a very strange thing because the double bond will attack the bromine, and the bromine in turn will attack the carbon, and the other bromine is going to leave. This is a little bit weird reaction because bromine itself is not polarized at all. The only way that a double bond will pick up a bromine is only if it was an electrophile, because remember the double bonds are nucleophiles. So this is a little bit of a different reaction, and this is the best mechanism that is possible, okay, to give the kind of products that we are expecting. So the double bond attacks the bromine, bromine attacks the carbon right back, and then here the bromine is leaving, okay, so which means we have a bromide ion in solution. So once this bromine is attacked by the double bond, it ends up forming this kind of a ring, which is a three-membered ring, and this is called a bromonium ion. If it was chlorine reacting, it would be called the chloronium ion, and you end up getting this kind of a cyclopropane or a three-membered ring. And what happens is, because this is a three-membered ring, the other bromide that has to come, it will come from the other side of the ring. And when it comes from the other side of the ring will open from the other side, which means from the opposite side. So which means that the two bromines that are added on, they will actually be added on onto the opposite sides. Okay, so when the bromide attacks over here, the bromonium ion is relieved and it gets its electrons, okay, and so you end up getting this bromine here, and then the bromide ion, which came from behind over here, is on the other carbon. So which means that the bromines are actually adding on opposite sides, and this is called a trans addition. This will happen whether you have straight chain or cyclic. It's a little bit easier to see on cyclic, that's why the mechanism is given here, but otherwise even for straight chain alkenes, that's the addition you will get. Now remember, the cis and trans, or this kind of an addition, the trans, can give you stereochemical products. In some cases you don't see that stereochemistry. So for example, here these carbons are not stereoactive, and so you will not see the trans addition in small molecules like this. But in some cases like cyclopentene, you will see the trans addition quite evidently. Now let's talk about the hydration of alkenes. Okay, hydration of alkene meaning that you are adding water to alkenes. For hydration, the product is alcohol. Okay, and so hydration means adding water, and you add water to give alcohol from the alkenes. Most of the hydrations are going to be acid catalyzed, and sometimes you would need a little bit of a reflux. Addition of water is going to follow Markovnikov's rule, which is that hydrogen goes to the carbon with more hydrogen. So here is propene, an asymmetric alkene. So if you add water to it, the hydrogen will go to the carbon with more hydrogen, and then the OH will go onto the other carbon. And here 2-methyl-propene, again asymmetric alkene, and so therefore the hydrogen goes to the carbon with more hydrogen. Okay, and so these are typical Markovnikov's addition. There are 3 hydration reactions that we're going to cover. The first one is the addition of water, and then there are 2 more coming up, okay, which are different reagents. So here's the mechanism for hydration, and again, since we talked about Markovnikov addition, the mechanism proceeds by carbocation formation. Okay, and so let's take the mechanism for 2-methylpropene. So here is the 2-methylpropene, 1, 2, 3, right? So the double bond picks up the hydrogen. Now remember the hydronium ion here. This is coming from the acid. Okay, so we have to have some little bit of sulfuric acid in there to protonate the water in order to make it a good electrophile. Okay, because water by itself is really not a very good acid. Okay, and since your alkene is reacting as the nucleophile, so your nucleophile needs a nice electrophile. So the presence of the acid makes the water a nice good electrophile. So here's the double bond picking up the proton leaves, and so you get water as a result over here, and then this double bond adds onto the hydrogen. Hydrogen goes to the carbon with more hydrogens, which is this. So again, Markovnikov addition, and you end up forming a tertiary carbocation. You could have also formed a secondary if this was a hydrogen, and that would have been fine, so long it's more stable, so long it's not primary. And then now we have a carbocation, which is the electrophile now. So the water, which is now become the nucleophile, will react with the carbocation, and then you end up getting this kind of addition. Now remember, I told you in class also that you should not get rid of anything unless you're ready to get rid of it. And so usually when you do these kind of additions with water, you should leave all the hydrogens on there and show the oxonium ion, okay, over here. So this is the new bond formed. Here you have oxonium. The last step will be the deprotonation of the oxonium, okay, over here. And so water comes in as a weak nucleophile, picks up this hydrogen, and that leaves then its electrons in the oxygen, which was positive, and now it is not positive anymore. So now we have the alcohol. Okay, so these are the steps that you have to take through. Again, this is a carbocation mechanism, and again you need an electrophile over here. What you have to keep in mind with the hydration also, just like with the addition of HCl hydrohalogenation, is that because this mechanism is going through the carbocation mechanism, you can also have rearrangement. I'm not covering another example for rearrangement because we covered it before, but because the mechanism is exactly the same, you should watch out for possibility of rearrangement of carbocation. The second reagent that we're going to talk about in hydration is what we call oxymercuration. Okay, and oxymercuration is where we use a mercury diacetate as a reagent, and this is followed by then NaBH4, sodium borohydride, in presence of a base. Now usually what happens is that whenever you do a reaction, you have the reagent and then you have the workup, okay, in the lab. And so the reagent here is the mercury acetate, and then once you treat it with sodium borohydride and base, that is the workup of the reaction, which means that helps to finalize the reaction. Okay, work it up meaning to protonate anything that is remaining to be protonated, so there are no ions left by the time you're done with the reaction. So in any case, what's the point of oxymercuration? The point is that it is a Markovnikov addition, and then there is no rearrangement. And why is there no rearrangement? Because the mechanism is not via carbocations, because carbocations give us rearrangement. The addition, however, is still Markovnikov, which means that the hydrogen will still go to the carbon with more hydrogen, but at least you will not get any rearrangement, okay, which is very much possible if you were just treating in an alkene with water, okay, in presence of an acid. So first of all, this is what the reaction looks like right here. If you have 1-pentene, asymmetric alkene, you treat that with mercury acetate. Mercury acetate here is on the top, the THFH2O. That tells you that you are using tetrahydrofuran, which is a solvent. And then here is how the intermediate forms, okay, where you have the OH on the less substituted carbon, or excuse me, the more substituted carbon, and the mercury acetate will attach itself to the carbon with the more hydrogen. So there is no formation of carbocation, and because mercury is so huge, it will like to stay on the terminal carbon, or it will like to stay on the carbon that is less substituted, so which means with more hydrogen. And then the workup is with the hydroxide ion and sodium borohydride, and what that does, it provides the hydrogen in order to get rid of the mercury, okay, or the mercury acetate. So that's where this hydrogen is coming from, because this is CH2 and now this is CH3. So then you end up getting this product. What happens to all of these other things as part of the reaction is that they actually all get washed out in water during the workup, okay? As far as I'm concerned, I need you to remember the reagent and the workup reagents, and that's it, okay? Don't worry about what happens to the rest of it. If it is important, I will mention it to you. So here then we have the mechanism for you, okay? So now we'll take a cyclopentene. Asymmetric, just to make it a point that you see that the reaction is Markovnikov addition, and this is how the steps are going through, okay? So you have the mercury acetate, which forms this kind of an intermediate, then the water comes in, and the water will attack, the OH will attack the carbon with more substituents on it, okay, which means again that the acetate is going, mercury acetate is going to the carbon with more hydrogens. And then sodium borohydride comes in and provides the hydride or the hydrogen to get rid of the mercury acetate over here. So that's what the reaction is happening. The other part I want you to see over here, and again, this is not so key for us right now, but sometimes it is important, is that the addition is anti-addition, okay, which means that the OH and the H that are adding, the H2O that has added on the opposite side. We did not have to talk about this in the hydration of alkenes with water because it was a carbocation formation. In carbocation formations, you end up getting racemic mixtures. And so we didn't talk about it before, but here you don't have a carbocation. So how is the addition taking place? Now, if you remember this intermediate right here with the mercurium ion, this is kind of the same thing as the bromonium ion. So if the bromonium ion was giving you a trans product, then here also you will end up getting a trans product, okay, so which is also called anti-addition, and that's what you get. Now in some cases, again, as I said, this is important, in some cases this is not important, depending on stereochemistry. The third hydration that we will talk about now is called hydroboration, and the key thing about hydroboration is that it is an anti-Markovnikov addition. The first two hydrations that we did were Markovnikov's addition, all right? But what if you don't want Markovnikov product? What if you want anti-Markovnikov product? Well, here is your answer, hydroboration. And you can thank Herbert C. Brown for this, because he's the one who came up with all of these reagents, and he got the Nobel Prize for this. So he's the one who came up with all of these borane reagents, which give very, very specific stereochemistry to generate alcohols, okay? And so the borane reagent that we are going to talk about here is just very simply borane, okay, hydroborane, and this is a pair of electrons, and this is THF, again tetrahydrofuran, all right, which is a solvent, and it helps to stabilize BH3, because if you remember, BH3 is a compound with incomplete octet, okay, and so the BH3 will kind of couple with THF to give it stability, okay, and then so after this reagent, then you treat it with a base in presence of hydrogen peroxide, and that will give you the anti-Markovnikov's addition of alcohol. The other thing about this reaction is that it's a syn addition. And again, these things are important when you're trying to generate a stereochemical center. All right. So for most of our reactions, we may not be doing it, but it is something to keep in mind that this reagent gives syn addition, which if you remember, the oxymercuration gave the anti-addition, okay, where the H and the OH were coming on opposite sides, but now they will be on the same side. Okay, so here is your reaction right here where you have cyclopentene, again methyl cyclopentene. You treat that with borane first and then with hydrogen peroxide. Now please, if we have to mind this, okay, if they're written as 1 and 2, it means that they are two-step reactions. You cannot add everything at the same time. So even in the previous one that we were talking about with oxymercuration, okay, you can't do everything at the same time. So you don't just take all of these reagents and put them in the reaction flask. You first have to do the first step, okay, which is the boration, and then the second step is after a while, when you're working up, then you treat it with hydrogen peroxide. So these are two steps and you must write them as two steps. And so once you treat them like with the alkene, you will get the alcohol. Now note that the alcohol group is on the carbon with more hydrogen, okay, and the hydrogen has gone to the carbon with less hydrogen, or the more substituted carbon. All right, so this is anti-Markovnikov addition, and this is another way of looking at it. We're going to do the mechanism in a minute on the next slide, but this is what it looks like, okay, where the intermediate is where it's called the organoborane, okay, and then the second step is where the hydrogen peroxide will come in and remove the borane from here. So let's look at the mechanism. First of all, borane is the Lewis acid, okay? And remember, alkenes are the nucleophile, or you can now consider them to be the Lewis base, okay? So this is a typical Lewis acid-base reaction. There is no traditional acid in this. Previously, we had HCl, H2SO4, but now we don't have any traditional, which means pronounced Lowry acid. Now we have a Lewis acid and a Lewis base reaction that is occurring. So here is your alkene, and here is the borane, all right? And so the borane will get attacked by the alkene, and it will end up giving this intermediate, okay? And this intermediate is what explains the reasoning behind the anti-Markovnikov addition, okay? And this is because we have boron over here. The boron over here is a little bit of a bigger atom than hydrogen, and so it will not come on the other side because there is steric crowding, okay, or there is steric hindrance. So because of steric hindrance, the boron has to go on the other carbon, all right, over here. And so because of that, you end up getting the anti-Markovnikov product. So the hydrogen, which means it's going to be attaching to the carbon with more carbons, or the more substituted carbon. And so when the peroxide comes along, then the peroxide will then remove the borane reagent and give the alcohol at that point. The peroxide and the base are the ones that are responsible for giving the hydroxide. I want you to keep in mind this hydrogen peroxide thing because I will talk about it later. Wherever you see hydrogen peroxide, it means that you're doing something unusual, okay? Because usually we use water for most part. We don't use hydrogen peroxide in many reactions. So whenever you see hydrogen peroxide, it means something unusual is going on, and unusual for us is usually anti-Markovnikov reactions, okay? One of the things that I would like to mention here also before I go forward, I've not given this in the PowerPoint, but the ratio of the alkene to the borane reagent is 1:3, which means 1 reagent, 1 mole of reagent, 3 moles of alkene, and that has to do with the fact that the boron can actually react with, or it has 3 reactive points, okay? So it can combine with 3 alkenes, okay, over here. So after this one, it can be attacked by another alkene to get rid of one of these hydrogens over here, and then 1 more, okay? So it can have 3 alkenes on 1 boron molecule, which makes it even more sterically hindered, which gives you even more of the anti-Markovnikov product, okay? That would be more if you were actually doing the reaction, then you have to mind the mole ratio. But right now, this is important that you know it is an anti-Markovnikov because of steric hindrance of the mechanism. Now for the next reaction, which is Hallow Hydrants, okay, from alkenes. Hallow Hydrants are addition of water as well as a halogen. Okay, so in this case here, this is what the reaction looks like. Is where you have an alkene, you're adding a halogen, where the halogen again is going to be chlorine or bromine. Remember, no fluorine or iodine, and then you're adding water also. And so what will happen is that on one carbon you will get a halogen, on the other carbon you will get an alcohol. So that's kind of what you end up forming, all right, over here. So the addition again is going to be anti, and we'll look at that in the mechanism, all right. The reagents that you start with first is bromine, and then you add water, okay, and or if you can add both of them together, that's also fine, okay, in this case. So here is how the mechanism works, okay. The first reagent to react is the halogen, not the water. So alkene will react with the halogen to give the halonium ion, which remember it could be bromonium or chloronium ion. So you form this kind of a three-membered ring. Once the three-membered ring is formed, then in comes the water, and it would attack from the backside, and that's how you get the anti-addition or trans-addition, which is the groups are on the opposite sides. So water will attack from the opposite sides, relieving the bromonium or chloronium ion, and then water will come in and deprotonate that oxonium ion, okay, from here, and you get the alcohol. So again, the halogen and alcohol group, they are anti to each other, and this is Hallow Hydrant formation. And the Hallow Hydrant formation tells you also that when you're trying to do halogenation, try not to have any water there in case you don't want any Hallow Hydrants. Okay, so it also tells you the reactivity of your alkenes. In some cases you may want to make this, but in some cases you may not want this. So in those cases you have to be careful not to have any water when you're doing any halogenation. Let's look at the mechanism of the Hallow Hydrant formation in case you have an asymmetric alkene, okay, or an unsymmetric alkene. Now, in the case of symmetric alkenes, not too many issues. The alkene will attack the bromine first or chlorine first, and then the water will attack. But the thing is that if you have an asymmetric alkene, then what happens? Okay, where does the water attack? The formation of the bromonium ion is not a problem because that is the first thing that will happen when you have an alkene and bromine or chlorine. Okay, so you will end up forming the bromonium ion. The question is that when the water comes in, where does it attack? Okay, does the water attack the carbon with more substituents or the one with less substituents? And here you have to think about Markovnikov addition again, except that in this case there is no hydrogen, okay, that is adding on. It's actually the bromine or the chlorine. So the halogen now will go to the carbon with more hydrogen, and the water will go to the carbon that is more substituted, again because the more substituted carbon is more likely to be the one that has the carbocation, okay, and so the water will then attack the carbon that is more substituted, and that's how you will get the alcohol on the more substituted carbon and halogen on the less substituted carbon, or you can say the halogen will go to the carbon with more hydrogen, okay, and so that's what the mechanism would be if you had asymmetric alkene in case of Hallow Hydrants. Now for the synthesis of diols. Okay, diols are two alcohol groups. Okay, and this is called hydroxylation also. And the addition here is syn. Okay, and this is something to keep in mind because this will come up again later on, but in a very different way. All right, and so the two reagents that are used here commonly are osmium tetroxide followed by sodium bisulfite. Again, this is the workup reagent. And then we can also use potassium permanganate, which is supposed to be used cold. Potassium permanganate is a very powerful oxidizing agent, and it has to be used very carefully. The only thing about potassium permanganate that is better than osmium tetroxide is that it's cheap. Osmium tetroxide is a precious metal and it's very expensive reagent. It's also a very toxic reagent. And so it's better to use KMnO4, but the problem with potassium permanganate is that it is a very strong oxidizing agent, which is why this reaction is done at room temperature or cold temperatures. And the other thing is that because it's powerful oxidizing agent, you may end up getting some side products you did not want. And then lastly, it's a little messy, okay? But otherwise, if you wanted a clean reaction, nice, and you have some money, use osmium tetroxide. KMnO4 This is also a qualitative test, and I will talk about this later on again. Okay. All right. So let's look at this reaction of formation of diols. So here is an alkene. Okay. And again, this is symmetric alkene. You're using osmium tetroxide. The solvent here is pyridine. And this is the intermediate that is formed. Okay. So where is osmium? And osmium can have up to 6 bonds. And so it forms the 2 oxygen bonds with the alkene over here, and then the sodium bisulfite will come and cleave this osmium from here, and the water will provide for the protons. Okay, again, so this is the workup reagent over here, and you will end up getting this diol. Now look at the stereochemistry. This is cis, and this is what we call a syn addition. It has nothing to do with you doing anything bad. The syn is SYN. And so this is a syn addition, which means that the hydroxy groups go on the same side, or whatever groups you're adding will go on the same side. Okay, potassium permanganate has the same kind of mechanism. So here we have the manganate ion. Again, manganate ion will attach to the alkene on the same side, and then it comes water with base, and you cleave the manganate, okay, from here, and you end up getting a diol. Again, it's a cis diol. The products are the same. The only thing is, again, as I said to you, that potassium permanganate is a very powerful oxidizing agent. So you end up getting cis diols. One of the things I would like to mention before I go on any further is the location of groups. Okay, so far we've done a few addition reactions, and I want to mention this to you before we get too far, because we might encounter some other kind of groups as we go on. When we add groups to any alkene or alkyne, there are 2 kinds of additions possible, vicinal and geminal. Vicinal additions are 1,2 additions, and these are on adjacent carbons. Geminal additions are additions on the same carbon. They're 1,1 or 2,2 or 3,3, whatever it is, but it's adding onto the same carbon. So vicinal additions, the 1,2 additions, will always appear like this, where you have the 2 groups that are attaching, and they are on adjacent carbons. Vicinal, vicinity, remember that, okay? So here we had the chlorine addition, the halogenation that we did, that was a vicinal addition. The diol formation is also a vicinal addition, okay? The geminal is when you get the addition on the same carbon, okay? And so, for example, if you were to add chlorine and it happened to add on the same carbon, that would be a geminal addition. And here you have the geminal diol, okay, where you have the 2 alcohols in the same group. All the additions that we have done so far have been vicinal additions. We will do geminal additions later on also, and so when I mention geminal to you, it will not be a foreign word, okay? But geminal means on the same carbon, vicinal means on adjacent carbons. Now we go on to something which is slightly different than what we've been doing before, and this is the reaction of alkene with carbines. So first of all, what is a carbine? If you take an alkene and you slice it into half, okay, which means that each of the carbon gets the pair of electrons that it has, because remember there are 4 electrons here, 2 pairs of electrons. So if one pair goes to carbon and the other pair goes to the other carbon, you end up getting something like this, okay, which means a carbon with a pair of electron. And that is what is called carbene. So which means that it is neither positive nor negative, but it has a pair of electron. It is considered to be electrically neutral. Okay, so which means again, no positive, no negative, it is just neutral, and it has a pair of electrons. That's how you identify a carbene. Anyway, so an alkene can react with a carbene to give a cyclopropane ring. Depending on what is attached on that carbene, RR, those RR can be hydrogens, or it could be other groups. Okay, and so this is what you end up getting. And again, this reaction is specifically to make a cyclopropane ring. If you did not want a cyclopropane ring, you would not use a carbene, because then this is the only reaction that is possible, okay, with the carbene and an alkene. So this is how you would generate a carbene, all right, which means that you take diiodomethane. Now remember, we haven't really used iodine before, but it's a very specific reaction. This is called the Simmons-Smith reaction, and in this case you will take the diiodomethane and you treat it with zinc and copper alloy, and once you do that, the zinc and copper will react with the diiodomethane to give you the carbene, okay, over here. And this carbene is right here actually, but it's bonded with the zinc also, all right, and that's why you can't really see it very clearly. So this is isolated for you over here. So once that carbene is generated, then it will go ahead and react with the alkene. Okay, so this is how you would actually write the reaction out, where you have the CH2I2 and then the zinc and the copper, and ether is the solvent over here. So the carbene that is generated as a result of these reagents will then just add on to the alkene. Addition is syn. Okay, as you can see from here, that we have the bonds going on the same side. They cannot be anti, okay, because it's such a small ring, you can't have the addition going on opposite sides, okay, and so this is a syn addition giving you a CH2. And this is another example of the addition of carbene, and this is dichlorocarbene. Okay, this is coming from chloroform, which is CHCl3, with in presence of a very strong base like potassium hydroxide. The potassium hydroxide will abstract HCl, okay, from here. Once it abstracts HCl from chloroform, all that is left is CCl2 with the electron pair. The CCl2 that is left over is what is actually adding over here. This is one of the reactions that you will be doing in your labs. I think it's in Organic 2, most likely. But in any case, this is what you end up getting. Now here, instead of hydrogens, you actually have chlorine. Which one you want to make is, of course, depends on what you need. Okay, so again, the addition is syn, and this is carbene chemistry. Now for the epoxide formation. In case of epoxide formation, you're forming a 3-membered ether with oxygen in it. Okay, again, very, very specific functional group that you're trying to make over here. And the reagent that we use for this is called a per acid. Per acid meaning something which has the maximum number of oxygens. Okay, that's what the per stands for, and it's an acid. So for example, if you take acetic acid would be CH3COOH, but now you have an extra oxygen in there. That extra oxygen makes this reagent a very good oxidizing agent and very reactive also, okay, for that matter. And so you can use any per acid to cause epoxidation. One of the common per acids to be used is perbenzoic acid, meta-perbenzoic acid, MCPBA, and this is what the structure looks like. Okay, we're going to do nomenclature of aromatics in Organic 2, okay, but this is the benzene ring, here is the chlorine, and here is the per acid part, okay, because benzoic acid is COOH, but there's an extra oxygen in here, and that extra oxygen is the reactive component, okay, of the per acid. And so if you have an alkene, it will add on to the alkene and give you an epoxide, and then you end up getting the acid as a result. So which means the extra oxygen is gone, now you just have an acid. You start with per acid, but now you have an acid. So this is epoxide formation. Again, the addition is syn because the small membered ring cannot be on opposite sides. Now for the hydrogenation of alkenes, which is the addition of hydrogen. And this is classified as both as an addition reaction as well as a reduction reaction. And so hydrogenation of an alkene will give us alkane. This reaction is quite common, but it's also very hard to do because it's very hard to get the alkene and the hydrogen to come in the correct orientation so that they can react with each other. So in order to help with that kind of a reaction, you need a catalyst, okay? And so you use platinum, palladium, nickel. These are all heavy metals in transition series, if you see, and they're used in order to catalyze this reaction. Okay, if they're not used, then this reaction is very hard to do because hydrogen is a very small diatomic molecule, and because it's very small and light, it's always moving around, and it's very hard for it to be in the correct orientation, okay, with alkene in order for it to react. So the platinum, palladium, or nickel provides the little background or the little surface, okay, that it needs to hold on to, and then it can do the reaction. Okay, so when you look at the reaction for any kind of hydrogen, okay, or any hydrogenation or reduction, you will see that you have the hydrogen there, but you also have a heavy metal there. The heavy metal may be as platinum oxide or palladium carbonate or something of that sort, but you will see a heavy metal in there, okay, and that means there is hydrogenation going on. The addition that we have for hydrogenation is also a syn addition, which means it's happening on the same side. And the mechanism can be explained like this in the diagram shown below, where you have the metal surface. The hydrogen actually bonds to the metal surface. It has specific affinity to these metals. That's why we don't use copper or cobalt or silicon or something like that, because these metals, platinum, palladium, nickel, these are the ones that bind very nicely with hydrogen. This process is actually called adsorption, which is AD, not AB, absorption, okay, adsorption. And in case of adsorption, the hydrogen is just on the surface of the metal. And so what happens then is the alkene will come around, and then it will also be on the surface of the metal. And once it's on the surface of the metal, it will just pick up the hydrogen and then move on. Okay, so which means that the hydrogens are being added from the same side. Okay, and so that's the role of the platinum palladium, okay, which is the role of the catalyst, is to give a linkage, okay, to the hydrogen, okay, which otherwise will move around. And that is also a reason why this addition is always going to be a syn addition or a cis addition. So one of the last reactions to do now for alkenes is oxidation. And this oxidation is not just oxidation, but it is actually oxidative cleavage, which means that you're also doing oxidation and you're also cleaving the alkene. We'll be using two reagents over here. One is with ozone, and the other reagent we will talk about is going to be KMnO4, okay, which is potassium permanganate, but this is going to be hot potassium permanganate, okay, so we'll talk about that. So the first reaction that we will do is with ozone. Ozone is the reagent. The workup is going to be with zinc and acetic acid, okay, so that's what you will see on the reaction arrow. On the top is ozone, and the second is zinc and acetic acid. In some cases, you might even see dimethyl sulfide. Depending on who is making the question and who's writing and who's using these reactions, you can use different kinds of workup reagents. But your main reagent is ozone, okay, over here. So here are two kinds of alkenes that we'll be working with, of course, the symmetric and the asymmetric, okay? So here, if you have this kind of a symmetric alkene, which is CH and then double bond CH2, then when you cleave that with ozone, you end up getting two aldehydes, okay? So what we're doing is just we are breaking this double bond, and in that double bond, you place oxygens, okay? So you end up getting two aldehydes in this case. When you have a carbon that is substituted, okay, on the double bond, and another carbon that is not substituted, then when you cleave this one, there's no hydrogen on the left carbon, so which means that you will end up getting a ketone, okay? If there was a hydrogen, then you would get an aldehyde, which is what you see here. So which means that if both of these were substituted with carbons completely, you will end up getting ketones, okay? So you can get aldehydes and ketones, and also ketones, okay? So depending on what kind of an alkene you have, not substituted, partly substituted to completely substituted, you can get different kinds of aldehydes and ketones. So make a note of that, all right? And so the mechanism here, which I don't need you to memorize the mechanism here, but just kind of see what's going on over here and how the double bond is breaking, is that here is the ozone, okay? And ozone will add on to the alkene, and this kind of a mechanism is like a concerted mechanism, okay, which means you don't know which arrow came first and which arrow came second. So in any case, this concerted mechanism will then cause the breakage of this bond, and then each carbon is going to get an oxygen, okay? Now if you look at the starting material here, the alkene, it's completely substituted, and because it's completely substituted, you're expecting ketones, okay? So here is one of the ketones, and then the other ketone will come from here once this fragment is worked up, okay? And it goes away with acetic acid, so you end up getting the other ketone, okay? So don't worry about all of this, because this is something that goes on in the reaction, but then once you work up the reaction, all of these intermediates will be gone. Here is the oxidation of alkenes with KMnO4. Now remember, we've done this reaction before with potassium permanganate to form diols. When we did this reaction with diols, we were careful enough to use cold temperatures or room temperature. In this case, what we're going to do is we're going to heat it up, okay, a little bit. So you can look at our reaction conditions, And so here is potassium permanganate in presence of a base and water and heat also. Okay, and you have to be careful to watch the conditions, because if you have KMnO4 cold, then you will get a diol, but potassium permanganate with heat will give you cleavage, okay, or oxidation. So you have to kind of watch out for that. All right, since potassium permanganate is a very powerful oxidizing agent, much more than ozone, it will give you even more oxidized products, okay, which means that we were stopping with aldehydes and ketones with ozone, but now here we can go all the way to acids. All right, let's look at this one first. Okay, here is a symmetrical alkene here with the CH and CH, which is also not completely substituted. So if it's not completely substituted and you have the hydrogens, now with KMnO4 you end up getting two acids, okay, over here. So in the previous case with ozone we ended up getting two aldehydes, all right, but now we're getting acids because KMnO4 is more oxidizing, more powerful oxidizing agent than ozone is, okay. However, if you get an alkene that is substituted completely, then you can't oxidize that more than a ketone, all right? So you have to stop at a ketone. This one cannot go on to an acid, all right? However, if you have a terminal alkene, which means you have a CH2 group, that CH2 groups will get oxidized all the way to carbon dioxide, okay? You will get the acid if you have another carbon, okay, attached to the double bond. But if you don't have that, if you have a terminal CH2, that will give you carbon dioxide. So everything about potassium permanganate is more oxidizing. This reaction is also a qualitative test, okay? But we're not isolating the products in qualitative tests. You could, okay? Because this is similar to what we did in diol, okay? Except that we're not heating it, okay? In diols here, you are heating it also. Here is an example of how we actually use the oxidative cleavage. Okay, it's a very good way of working through structures of compounds. Okay, so for example, if you have an unknown alkene with a molecular formula of C7H12 and then you treat it with KMnO4, then you end up getting this product. Okay, in this case, you have a ketone over here and then you have an acid. So you have C7H12. Okay, that's your starting material, your unknown alkene, okay, with this molecular formula, and with KMnO4 it is giving you this product. So what is the structure, okay, of this product? So what you do is count your carbons first of all, okay, make sure that you have 7 carbons, which is 1, 2, 3, 4, 5, 6, 7 carbons, okay, and the fact that you have a COOH, which means if you have an acid, it means you have to have a more oxidized carbon, okay, which means a less substituted carbon. So the ketone is coming from a more substituted carbon and an acid is coming from a less substituted carbon. And the other fact is that because you have only one fragment, it means that you're starting with a cyclic structure. If you had a straight chain alkene, you would have 2 fragments at the end, but because you're starting with one molecule, which is cyclic, you're getting only one molecule at the end with the 2 functional groups. So now all you have to do is attach these 2 carbons where you have the double bonded oxygens, okay, and that's where the double bond is going to be. And so this is your starting material, okay, for this. So here's the CH3, that is the CH3. So this is the one, this is the carbon that gave us the ketone, and this is the carbon that gave us the carboxylic acid. Okay, so that's how you kind of work this through. Okay, and I'll work some more problems with you in class. So now that you know all the reactions for alkenes, let's talk about the qualitative test that I mentioned to you as we were going on. Qualitative tests are done to distinguish functional groups, okay, from one to the other, because almost all organic compounds will look like water, which means clear and colorless, all right? And so to determine what functional group you have, you do qual tests, okay? And so qual test, as you have learned before also in Gen Chem, should be nice and visual, okay? Something that you can see either a color change, precipitation, things like that, okay? So here the 2 qual tests that we have done are addition of bromine and addition of potassium permanganate. So bromine is a dark colored liquid, okay, and when you add that to the alkene, the bromine will add to alkene. If it is adding to alkene, the bromine is disappearing, okay, which means that the dark color of bromine is disappearing. So which means that the bromine color disappears then you have an alkene. So that is your positive qual test, okay, for an alkene, that there is disappearance of the red color. In case of potassium permanganate, we learned two reactions. One was the synthesis of diol and the other one was oxidative cleavage. It doesn't really matter which reaction you do, because in either case you have the presence of an alkene. So we generally do this at room temperature instead of heating it up, because there is no need to. So potassium permanganate is a beautiful purple colored solution. Okay, we made this in water. It's a beautiful purple colored solution. When you add that to an alkene, it will oxidize the alkene. And if it is oxidizing the alkene, it itself is getting reduced during the process. And the product that you get is MnO2, because two of the oxygens are gone to the alkene. And so it will give MnO2, which is manganese dioxide, and that is also brown in color. Not only brown, it is also a precipitate. Okay, and so at the end of the reaction, you will see a brown precipitate and disappearance of the purple color. So that is your positive for alkene. So these two reactions are very useful, not only in the lab, but also in solving for some questions. Okay, and let me give you an example. So when we have an alkene, like the problem that we just did, okay, where you are given a molecular formula and you're trying to figure out the structure of that molecular formula, these tests really help, because if you have one hydrogen deficiency index in a molecule, but it is not adding any bromine, that tells you you don't have any alkene, right? However, if you have two hydrogen deficiency index or a hydrogen deficiency index of 2, but you're absorbing only 1 mole of bromine, it means you have one ring and one alkene, all right, in there. So it helps to give you a little bit of a framework to work with, okay, when you're trying to solve that puzzle. So we'll do some more examples in class so you understand that part. So you can see from this chapter that we have a lot of things to remember. Okay, there'll be a lot of reagents and a lot of little things to remember, like Marconic oxidations, syn additions, anti-additions, some of the mechanism. Then you have to also worry about the rearrangements that we did with the hydrations because of the carbocation formation. Hallow hydrant, where does the OH go? Okay, to the more substituted carbon or to the less one? Carbene epoxides are very much reagent based, so you have to remember those. And then hydrogenation and diols, and then finally oxidative cleavage. Oxidative cleavage is the most fun one because this is more like a puzzle, okay, where you will have to figure out what the products are, and in some cases, kind of like the example that we just did, okay, where you had the molecular formula and you have the products and you have to figure out what the starting material was, okay, or the molecule was. So these are the things that you should know. I know it's huge, but I know you can do it.